Hi, everybody. It's Professor Mitchell, continuing with Chapter 3. In this video, we'll be looking at Section 3.3 on the fundamental theorem of linear programming. In this section, we'll talk about the vertex of a feasible set. We'll talk about the fundamental theorem of linear programming, and then we'll go over the steps of solving a linear programming problem. So a vertex is defined as follows. The boundary of the feasible set is composed of line segments. The line segments intersect in points, each of which is a corner of the feasible set. Such a corner is called a vertex. So here is the feasible set that we developed in the last section. So in this example, we're going to find the vertices of this feasible set. Now, you may remember that in the last section, I did not put the inequalities in standard form because I don't do it that way. However, since they already have them in standard form, in order to avoid going back to the last video, I will just use the inequalities in this form to find the vertices. So let me switch over to the tablet. You might be able to hear my cat there. He's looking for attention. All right, here we go. So I've done my best to sketch this feasible set, and I've also labeled the boundary lines, and I've also labeled the vertices with letters A, B, C, D, E. Okay, so starting with vertex A is pretty clearly just the origin, 0, 0. Okay, so moving on to vertex B. Vertex B is the y-intercept of the line y equals negative x over 3 plus 12. So that would be the point 0, 12. Okay, and after that, they get just a little bit more complicated. So let's look at vertex C. Vertex C is the intersection of the lines y equals negative x over 3 plus 12, and y equals negative x plus 18. So I'm going to set those two expressions equal to each other, and because this equation contains a fraction, I think it might be helpful to multiply both sides by 3 in order to get rid of that fraction. So that is going to give us negative x plus 36 equals negative 3x plus 54. So now I will add 3x to both sides. And while I'm at it, I will subtract 36 from both sides. So this is going to go away, this is going to go away, and we're going to be left with 2x equals 18, which means x equals 9. All right, so the x coordinate of that point is 9. To get the y coordinate, we just substitute that x value into either one of the equations. I think I will pick y equals negative x plus 18. Since x is 9, that gives us y equals negative 9 plus 18, which is 9. All right, so x is 9, y is 9. Vertex C is the point 9, 9. All right, so that brings us to vertex D. Vertex D is the intersection of the lines y equals negative x plus 18 and y equals negative 2x plus 32. All right, so this equation's a little simpler. We'll add 2x to both sides and then subtract 18 from both sides. Which leaves us with x equals 14. And once again, I'll substitute that value into the equation y equals negative x plus 18. Y equals negative 14 plus 18 comes out to 4. Vertex D is the point 14, comma 4. All right, and that brings us to vertex E. Vertex E is the x-intercept of the line y equals negative 2x plus 32. So we just substitute 0 for y. And now if we add 2x to both sides, that'll give us 2x equals 32, which means x equals 16. And of course, y is 0 because this is the x-intercept. So vertex E is the point 16, 0. And we have all of our vertices. So now we'll go back to the presentation. All right, so here we are. We found all these vertices. Okay, so the next question is, what do we do with them? Well, that question is answered by the fundamental theorem of linear programming, which says that the maximum or minimum value of the objective function in a linear programming problem is achieved at one of the vertices of the feasible set. So remember, this problem came from manufacturing chairs and sofas. So these vertices, one of these vertices has to be the solution to the problem of maximizing profit. It'll tell us how many chairs and how many sofas to manufacture in order to maximize profit. The point that yields the maximum or minimum value of the objective function is called an optimal point. Now, I need to mention something else, which may or may not be addressed somewhere else in the PowerPoint, which is that you're not always going to have a maximum or minimum value. In this case, because the feasible set is bounded, that guarantees both a maximum and a minimum value. If you have an unbounded feasible set, which we sometimes will, there may or may not be a maximum or minimum value. Okay, so just something to keep in mind. All right, so now we'll finally finish off this problem of manufacturing the chairs and the sofas by finding the point which maximizes profit, which remember was 80x plus 70y, for this feasible set, which has these vertices. So all you have to do is just make a chart, list all the vertices, and then plug all the vertices into the objective function. Notice that 0, 0 gives you the minimum value. Obviously, if you don't manufacture any chairs and any sofas, you're not going to get any profit. So that's not the point we're interested in. However, if you look at these other vertices, you see that the maximum value for the objective function is 1400. That happens when x is 14 and y is 4. In other words, to maximize profit, you should manufacture 14 chairs and 4 sofas. All right, so now let's go over the steps of solving a linear programming problem, and then we will do another example. Step 1 is to translate the problem into mathematical language. That means organizing the data, identifying the unknown quantities, and defining corresponding variables. Translate the restrictions into linear inequalities. And finally, form the objective function. Step 2 is to graph the feasible set. I'm going to skip letter A here because I usually don't put the inequalities in standard form, and I will not be doing that in the example that's coming up. Graph the straight line corresponding to each inequality, and then determine the side of the line belonging to the graph of each inequality. And we'll cross out the other side. The region that's left at the end is the feasible set. Step 3 is to determine the vertices of the feasible set. And finally, step 4 is to evaluate the objective function at each vertex and determine the optimal point. All right, so our next example is a minimum problem, problem involving nutrition. Rice and soybeans are to be part of a staple diet. 1 cup of uncooked rice costs 21 cents and contains 15 grams of protein, 810 calories, and 1/9 of a milligram of vitamin B2. 1 cup of uncooked soybeans costs 14 cents and contains 22.5 grams of protein, 270 calories, and 1/3 of a milligram of vitamin B2. The minimum daily requirements are 90 grams of protein, 1,620 calories, and 1 milligram of vitamin B2. We want to design the lowest cost diet meeting these specifications. In other words, find the optimal point that will minimize cost. So first we'll organize the data. Across the top, we have rice and soybeans, along with the required level per day. And then down the side, we have our nutritional requirements. We need a certain amount of protein, a certain amount of calories, a certain amount of vitamin B2. We'll identify the unknown quantities and define the corresponding variables. So the unknown quantities are the number of cups of rice and the number of cups of soybeans. So those are going to be X and Y. And now we'll translate our restrictions into linear inequalities. So the first one will represent protein. We need at least 90 grams of protein per day. So that turns into 15X plus 22.5Y is greater than or equal to 90. Notice in this problem, it's greater than or equal to 90. It's okay if you get more protein than what's required. You just can't have less. Same kind of thing for calories. 810X plus 270Y is greater than or equal to 1620. And vitamin B2, 1/9 X plus 1/3 Y has to be at least 1. And as usual, the variables cannot be negative. X and Y both have to be greater than or equal to 0. All right, and then the objective function is cost. We want to minimize the cost. Each cup of rice costs 21 cents. Each cup of soybeans is 14 cents. So cost would be 21X plus 14Y. Okay, now I'm going to skip this part, and I think I'll just go over to the tablet, because where we're going with this is we're going to graph our feasible set. All right, so here are all of our inequalities. Okay, so I'm going to graph all of these inequalities, which will give us our feasible set. So I'm going to start with protein. First thing we need is the boundary line, 15X plus 22.5Y equals 90. I will get the intercepts. That's usually how I do it. So the x-intercept is where y is 0, which leaves us with 15x equals 90. In other words, x equals 6. And the y-intercept, setting x equal to 0, is 22.5y equals 90. Dividing both sides by 22.5, we are left with y equals 4. All right. Now I'm tempted to graph these as I go along, but I think it would be better to wait until the end, because that's going to help me decide how to scale my X and Y axis. In some of these problems, your X or Y intercepts or both tend to be kind of big numbers. So you may not want to go with the usual just 1, 2, 3, 4, 5 for the tick marks on your X and Y axis. Okay, moving on to just thinking about color coding these. Moving on to the next one, 810x plus 270y equals 1620. Starting with the x-intercept, set y equal to 0. That gives you 810x equals 1620. Dividing both sides by 810, you get x equals 2. And then the y-intercept is where x is 0. 270y equals 1620. Dividing both sides by 270, you get y equals 6. All right. Let me see. I think I left myself another blank screen. Yes, I did. So that brings us to the vitamin B2 inequality, whose boundary line is 1/9 x plus 1/3 y equals 1. That line has an x-intercept where 1/9 x equals 1. Multiplying both sides by 9, you get x equals 9. And the y-intercept, which is where x is 0, gives you 1/3 y equals 1. Multiplying both sides by 3, you get y equals 3. All right. So I think we're ready to start graphing this thing. It doesn't look like I have to do any really weird scaling for this one. X is as big as 9 and y is as big as 6, I think. All right. So let's start with x equals 6, y equals 4. Okay. I do need to be kind of careful. You know what? Hold on just a second. All right. Yes, this will be helpful. It just occurred to me to see if I have a different sort of grid I can use. This one will work. Okay. So let me just look one more time. So the red line is going to have x equals 6, y equals 4. So that line looks something like this. And then the blue line has x equals 2, y equals 6. X equals 2, y equals 6. And finally, the green line has x equals 9, y equals 3. Okay. This should work out very well. Okay. So now let's talk about which sides we're going to cross out, starting with the red line. Actually, might be able to get this all done pretty quick. Let's start with x equals 0. I mean, x is greater than or equal, x is greater than or equal to 0. Y is greater than or equal to 0. That just means that the whole feasible set has to be in the first quadrant. That's how I'm able to get away with using this particular grid, because it only shows the first quadrant. So you can imagine crossing out all of this stuff over here, all of this stuff over, oops, here. Okay. All right. And now let's talk about our other inequalities. So for all of those inequalities, we can use 0, 0 as a test point because 0, 0 is not on any of those lines. If I put that into the first inequality, I get 0 is greater than or equal to 90, which is false. Into the second inequality gives me 0 is greater than or equal to 1620, which is false. And into the third inequality gives me 0 is greater than or equal to 1, which is also false. So with respect to each one of these lines, we're going to cross out the side that contains 0, 0. So we'll get rid of this. We'll get rid of this. And we will get rid of this. All right, so hopefully you can see what's left. I will outline it here for you. This feasible set has as its boundary this line, and then it makes a little turn. Let me try that again. Okay. That intercept is just a little bit off. Okay. So the boundary looks like this. All right. This feasible set has 1, 2, 3, 4 vertices. So now we need to talk about what are the coordinates of those vertices. All right, so to keep this video from getting any longer, I am not going to show all the details of finding the vertices. I do encourage you to pause the video and try to find them and then come back and compare notes. All right, so first we have the y-intercept of the line y equals negative 3x plus 6, which is 0, 6. And of course, they've written the equations in standard form, which I didn't do. The intersection of the lines y equals negative 3x plus 6 and y equals negative 2/3 x plus 4, which comes out to be sort of a fractional point, 6/7, 24/7. The intersection of the lines y equals negative 2/3 x plus 4 and y equals negative 1/3 x plus 3 is the 0.32. And finally, the x-intercept of the line y equals negative 1/3 x plus 3 is the 0.90. So those are our 4 vertices. So now we'll determine the objective function at each vertex and determine the optimal point. All right, so it turns out, remember, we're trying to minimize cost in this problem. So the minimum cost is achieved when you use 6/7 of a cup of rice and 24/7 cups of soybeans. 24/7 would be what, 3 3/7, for a total cost of 66 cents. All right, and that's going to do it for this section. The fundamental theorem of linear programming states that the optimal value of the objective function for a linear programming problem occurs at a vertex of the feasible set. To solve a linear programming word problem, assign variables to the unknown quantities, translate the restrictions into a system of linear inequalities involving no more than 2 variables. In the next chapter, we'll talk about how to solve these problems when you have more than 2 variables, by the way. Form a function for the quantity to be optimized, graph the feasible set, evaluate the objective function at each vertex, and identify the vertex that gives the optimal value. And that's going to do it for this section. We'll see you next time.